For the very beginning of this lab, we set up a beam expander, just like in the previous lab. We have a 0.25 NA objective, a 10 micron spatial filter, and a 250 millimeter focal length collimating lens. We had to make a few compromises. We couldn't get the 0.4 NA microscope objective to work, and we didn't have enough 5 micron spatial filters, so we switched to these. And then we also only had 250 millimeter collimating lenses, so we were unable to expand the beam as much as we wanted, but these are the equipment that we had.
So this is some of the theory behind the shear plate interferometer. If we had one with no wedge, if the beam is collimated, then we'd be able to see just this blank pattern, and at defocus locations we'd see fringes, but they'd all look the same, whether it was inside or outside of focus. Thankfully, we had one that had wedge in it, so when it's at a collimated location, our fringes would be in line. If it's on either side, the angle would show where we are relative because it adds tilt into the system. So that made it easier for us to find where the better collimated location is. So this is a little more about the shear plate interferometer. The beam comes in and then reflects off. So this is the beam diameter, this is the shear distance, and the fringes, this is the fringe spacing. And knowing these variables, we can calculate the defocus in waves in our system. After calculating the defocus in waves and also measuring the angle of the fringes, we can calculate the wedge angle in the interferometer.
For the first two sections of the lab, we used this equation to find the focal length. So we can find the focal length of either the lens or the mirror dependent on the radius that we determined from the fringes on our shear plate and the length or the distance between the object we're testing and the shear plate.
So in this part of the lab, we are measuring the near flat mirror. So we have it at one location, and we measure the shear distance, the fringe spacing, and the angle. And then we put it way far back at another location and do the same thing. Since the fringes are not parallel with the line, we know that it's not a flat mirror, and since our fringes don't really change, we know that it's a very long focal length or near planar mirror.
In this next section of the lab, we're going to be testing the power of a low power lens. So first we have to turn our shear plate back around to its original position, and then we're going to place our lens that we're testing in front of the shear plate. Then we can simply measure the shear distance, angular deviation, and spacing of the fringes that appear on the shear plate, just as we did in the previous part of the lab.
This is the theory behind finding the focal length of the curved mirror. We have our two positions. Our first position is usually known as cat's eye, where the mirror is directly at the focal point, which causes the rays to reflect back, and you end up with collimated light coming this way. The second position is when you match the wavefront with the curvature of the mirror, as shown here. And if you do that, you get another plane wave reflecting back that way. And you can use the distance between these two locations is the radius of curvature, and you divide that by 2 to find the focal length. And so we turn the shear plate 180 degrees so that the light could pass through, and then we put a reference line in so that it would focus the light to a focal point. And then the first, we put this in two different positions. The first one we lined up at the focal point, which did give us straight line fringes here, and then we moved it back to when the wavefront matched with the curvature of the mirror, and we should also have gotten, which we did, straight line fringes again. And the distance between those two positions would be the radius of curvature, which we found to be 20 centimeters or 200 millimeters, and half of that is the focal length, which means this is a 100 millimeter focal length mirror, which matched the specification on the bottom. So here our mirror is at the focal point of the reference lens. Then we move it all the way back so that the radius of curvature matches.